Ma'am, can we do it on 28th, ma'am, if it is possible?
28th, Monday, you're saying? Monday again at 5:30?
Ma'am, not 5:30, 6 o'clock, ma'am. 5:30, like 6 o'clock.
So actually 6 o'clock, I don't have any problem with 6 o'clock, but the other faculty actually he doesn't. So he was saying that it would be better for him if we could have the quiz at 5:30. That's why this time we had thought that we'll prepone the quiz from 6 to 5:30. So have classes till 5:30?
Yes, no problem, ma'am. At 5:30 also we'll do it, ma'am, because from 4:30 to 5:30 we have our last class on Monday.
4:30 to 5:30. Okay.
So after 5:30, like on 5:30 also, if it is possible, 2-3 minutes.
But you're saying that to do it on Monday, 28th.
Yes.
Okay. Okay, so then let me talk with the. But then we have to see about that other the other section also, na?
Ma'am, actually for other section also the quiz on there is a quiz on that day, ma'am.
Okay, so you have the same quiz of the same subject for both the sections.
Yes, ma'am.
Okay, fine. Then I don't think it should be an issue, but just give me today's time. I'll cross check with the other faculty and then let you know whether it's possible to. But I don't think there should be any problem to do it on Monday. Okay.
Yes, ma'am.
So just give me today's time. I'll discuss with him and then I'll let him. So good morning, everyone. Let us start today's class. Okay, the screen is visible, right?
Yes, ma'am.
Okay, now just hold on for 1 second. Okay, so in the last class we were talking about this how to. Mostly we were talking about when we have when you are representing a system using state space representation, that is in a vector form. So in that case, if you want to find out what would be the transient response or time domain response of that system for a particular type of input, so how would you solve those equations? Because if you have a differential equation, if you can express your the dynamics of the system in form of a differential equation, then you know that it's easier to find. You can take the you can take the Laplace transform, you can take the inverse Laplace, and then find out what would be the time domain response. But the moment you have been given with, so that was the case when we had a single input to your system and the output was also a single output. Okay, and the system order was lower and it was a smaller system. But in case if you have a larger system and you are representing the system using the state space model, so in that case obviously we are selecting different state variables and we are finding out what would be the values of these state variables in the time domain. So for that, what we needed to do is that we had to find out what would be a matrix which is known as the state transition matrix. So using the state transition matrix, we can find out the overall response of the system towards a specific type of input. So if your input is a step input or a ramp input or something else, so depending on the, so we have found out there is an expression, we have derived the expression for what will be the value of xt in terms of the state transition matrix as well as the input input signal which is provided to you. So now today we'll look into something, two different concepts which are known as controllability and observability. Okay, so basically this concept of controllability and observability, this comes whether, so if you have a control problem, okay, so we need to actually ask two basic questions, or two basic questions need to be answered in case we want to analyze or we want to infer that whether a control solution or a solution to that whole problem that it exists or not. Okay, so what are these two questions? So the first question is that can we transfer the system from an initial state to any other desired state in a finite time by application of a suitable control force. So if you apply a suitable control force, as in a suitable input, so after application of that suitable input, whether we can transfer the system from the initial state to, let's say, a desired state, if this is possible or not. If this is possible, then we say that okay, the system, then we say that a solution to that kind of a control problem exists. Also, there is another question, that is that we need to, so if we know the output vector for, or the output matrix, you can say, if we know the output vector or output matrix for a finite length of time, so for, let's say, for time t equals to 0 to t equals to some t0 or t equals to something t1. So if we know the output during that finite amount of time, so is it possible to determine the initial state of the system? That means that can we backtrace the initial state of the system, given that we know given that the output of your system for a finite duration of time is known. So these two questions are very important. So these, like, this is from a physical point of view, that if you can answer these two questions, then we say that okay, that the proper control solution exists to that problem. Okay, so now these are like very you can say these are like abstract kind of a concept. Okay, so how would we express them in a mathematical form? Okay, so this answers to these questions, they were actually conceptualized by someone known as Kalman. So what he did was that he said that he said that a system is said to be completely state controllable if it is possible to transfer the system from an initial state xt0. Okay, so if you have this xt0, one second. Okay, so the answer to the first question, that is if it is possible to transfer the system from an initial state xt0 to any other desired state, let's say xt, within a finite duration of time by application of a suitable control vector ut, where control vector is basically the input to your system. If this is possible, then we say that the system is known as completely state controllable. Okay, so this is the concept of controllability. So you say that a system is completely state controllable if we can transfer the system from an initial state to a desired state by application of a suitable control vector. And if you want to answer the second question, so we say that a system is said to be completely observable if every state xt0 can be completely identified by measurement of the outputs, that is yt, over a finite time interval. That means we can backtrace from the output, we can backtrace what would be the value of every state at the initial condition, that is at t equals to t0. Let's say if we say that the initial state, let's say it occurs at time t equals to t0. Okay, so if we can measure, if we can quantify the value of the initial state of the system by measurement of the outputs, that is yt, over a finite time interval, if this is possible, then we say that the system is completely observable. So these two are the two concepts of controllability and observability. Okay, so now, so this controllability now, so that means the controllability, it depends, or it involves the dependence of the state variable on the state variables of a system on the inputs. Okay, so let's take an example. Let's say that if you have a linear, a single input linear time invariant system, let's say the state equation is given by x dot equals to ax plus bu. So where x is basically your state vector. So let's say that it is an n-dimensional state vector. U is the input or the control force. A is the system matrix, or this is, let's say, an n cross n matrix, and B is an n cross 1 matrix. Okay, so now if the initial state of the system is given by x0, and let us say that after time t equals to tf, we want that the desired state of the system should reach some value x at tf, t equals to tf. Okay, so the system will be controllable if it is possible to construct a control signal, if you can find out a suitable value of ut such that within a finite time interval, that is from t equals to 0 to t equals to tf, within that finite time interval, if you can transfer the system from the initial state, that is from x0 to the desired state, which is xtf. If this is possible, then we say that the system is completely controllable. Okay, so now let's try to see it from a mathematical point of view. So now let's say that the system that we already have, that is x dot is equals to ax plus bu. So this is the state equation, original state equation, which is provided, and we assume that all the eigenvalues of this system matrix A, they are distinct. Okay, so now what we can do is that, so now let us transform this state equation. So this A is, let us say that initially A is a non-diagonal matrix. Okay, so what we would want to do is that we want to transfer, or we want to transform this matrix A from a non-diagonal form into a diagonal form. Okay, so that means if you remember the concept of diagonalization, so the process of diagonalization, it states that the process of converting a non-diagonal matrix using a suitable transformation to a diagonal matrix, that is known as that was known as the procedure called diagonalization. Okay, so similarly we can so let us say that we use a linear transformation x equals to m into v, and using this linear transformation, what is happening is that this A, the system matrix, now it is becoming we are expressing the system matrix in form of a diagonal matrix. Okay, so if you simply substitute the value of x equals to mv, so from here you can write on the left hand side, you will have m into v dot will be equals to a m into v plus bu, right? So if you write the expression of v dot, so v dot will be equals to, so v dot will be equals to m inverse a mv plus m inverse b into u. Okay, so this we can simply write this m inverse a into m, we can substitute it by capital delta, and we can substitute m inverse b by this quantity b bar. Okay, so we can write this expression in this form. So in this transformed form, we have this capital delta. This is basically a diagonal matrix. Okay, and the value of this capital delta is given by m inverse a into m. So we have to select m. So m, if you remember, m was known as the modal matrix. Okay, so we have to select the value of m in such a way that m inverse am, this value is basically a diagonal matrix. Right, so from this state equation, what we can do is that we can simply expand it and write it in matrix form. So v dot will be equals to, let's say, since we are dealing with an n cross n matrix, so there will be like n number of, so there are like n number of state variables. Right, so the transform state variables are, let's say, v1, v2 till vn. So we can write on the left hand side, you have this matrix v1 dot till vn dot. This lambda capital delta is basically a diagonal matrix, and the elements of the diagonal elements are nothing but the eigenvalues of the matrix A. So the diagonal elements are lambda 1 till lambda n. And this is the state variable. So the modified or the transformed state variable is v1 till vn. And similarly, we can write this b bar is basically b1 till bn bar multiplied by u. Okay, so you can simply write this equation. So this is in the vector form. So you can write the individual equations also. So you will get n number of differential equations from this vector form. Okay, so you can write this in this form. So Vi dot will be equals to Vi multiplied by lambda I plus Bi bar multiplied by U. So here you see that we have only since only the diagonal elements are present. So that means all the other states which are present in your system, they are not actually affecting the value. So you will have only the values of the eigenvalues multiplied by the corresponding state vector. So you have Vi dot will be equals to Vi into lambda I plus Bi bar into U. Okay, and this is the form of the state equation, and we can find the solution to the state equation which will be written in this form. So this we have done in the last class, where we had seen that the value of xt was equals to e to the power at multiplied by x of 0 plus e to the power at integral 0 to t some phi t, something like that. So we have found out that this expression, so this is the solution of this differential equation. So you can write Vi in terms of e to the power lambda it. So where e to the power lambda it is basically the state transition matrix that we have, or you can say that this is the matrix polynomial, you can say. So this is the e to the power lambda it into Vi0 plus e to the power lambda it integral e to the power minus lambda I into, so this would be tau B1 bar into U tau d tau. So the solution for this equation is given by this. Okay, so now you can say that this system is completely controllable if this Vi can be transferred from the initial state was Vi0, and let us say the desired state is Vi at time t equals to Tf. Okay, so if you can transfer, so the system will be said that it is completely controllable if the state variable Vi can be transferred from its initial state, that is Vi0, to the final state or to the desired state, you can say, to a final or desired state, which is Vi of Tf within a finite time interval of Tf. If this is possible, then we say that the system is completely controllable. Okay, so now if your system is completely controllable, then it will, so in other terms you can say that it is possible to construct, if it is possible to construct a control signal ut such that this condition is satisfied. So this condition we will write from this solution. So we will have Vit minus this thing divided by this e to the power lambda it will be equals to this. So from the previous equation, if this condition is satisfied, then we say that the system is completely controllable. Okay, so that means that the necessary and the sufficient condition for your system, for a system to be completely controllable, is that this vector, so Bi bar is basically nothing but the elements of this matrix. Okay, or elements of this vector. So if if the vector B bar, this does not have any row of 0 elements, then we say that this condition will be satisfied, and this is the necessary and sufficient condition for the complete controllability of your system. In case if one of the elements, or if any elements of this vector B bar is equals to 0, then we say that the corresponding, that particular to that element, the corresponding state which is present, that is not controllable. So since we have like n number of states in our system, so in case if you have the in case all the elements of this matrix B is not equals to 0, then we say that all the states in your system are controllable, or the overall system is completely controllable. But if a particular value of B bar is equals to, so let's say that B2, this thing is equals to 0. If this is equals to 0, so that means the corresponding state variable, which the corresponding state variable will be V2. So this corresponding state variable V2, that is not controllable. So this is the, so if you can find out this matrix B bar, then you can say from the, if you analyze this matrix, then from analysis of that matrix, you can say whether your system is completely controllable or not. Okay, so that means that whenever you are given with a system, so what you have to do is that you have to find out the, if you want to find out the controllability property, or if you have to analyze the controllability of the system, so you need to find out the vector b bar. So finding out the vector b bar means you have to find out that you have to find out this modal matrix M. You have to take an inverse of that modal matrix, multiply it with B, then you will get this matrix. So this becomes a little, this is also possible, but this is a little, you can say a little tedious process, or it requires a little bit more computation. Okay, so if you have an higher order system, then if you have like nth order system, then computing this matrix becomes a little time consuming. So in order to cater to that kind of a problem, what has been done is that Kalman has actually suggested something else. So this is an alternative method to test the controllability of a system. So this is a Kalman test, you can say. So in case if you have a general nth order system, nth order multiple input multiple output system, so and the control vector is an m-dimensional control vector. Okay, so that means the state equation is given by this: x dot is equals to ax plus bu. Okay, so either what you can do is that first of all you can do the transformation, you can find the modal matrix, you can find the value of this b like this and analyze whether any element of this matrix is equals to 0 or not. From there you can find out what will be the or from there you can comment on the controllability of the system. But the alternate way is that, suppose what Kalman has said, that this system which is represented by this state equation, this will be completely controllable if and only if the rank of a composite matrix QC is equals to n. So n being the nth order, n being the order of the system. Okay, so and this QC is basically, this composite matrix QC is defined as B. So we define QC as a matrix where in the first so this is a basically, you can say a row matrix, you can say, and where each element of the row, they are, so the first element is B, the second element is AB, then so on and so forth till the last element is a to the power n minus 1 into B. Okay, so that means that in this case you don't need to find out this modal matrix, do the inverse. So this step is now not required. So you can simply find out this matrix QC from here. So and then once you have computed this matrix QC, if you see that the rank of this matrix is equals to n, then you say that the system that is provided to you is completely controllable. If the rank of the matrix is not equal to n, then you say that the system is not completely controllable. Okay, so now here you see that you have only two matrices which are involved. So you have only matrix A and matrix B. So since only two matrices are involved in this case, so you can say that the pair AB, so this matrix pair AB is controllable if the rank of QC is equals to n. If this condition is satisfied, then you say that the system is completely controllable, as well as you can say that the pair AB, the matrix pair AB, that is completely controllable. Okay. So now let's try to do a problem, and then it will be a little bit more clear to you. So we'll use two different, both the methods. Okay, so the first method is, so you have been given with this kind of a state equation, and you have to find out whether the system is completely controllable or not. Okay, so if you use the first method, so that means that if you find out this matrix B and you see whether you analyze whether the elements are all non-zero. So if you want to find out this, so that means that first of all, this is the matrix A, this is the matrix B. So here you see that A is a non-diagonal matrix, so we need to transform it into a diagonal form. Okay, so in order to transform it to the diagonal form, so what we need to do is that first of all we have to find out the eigenvalues of this matrix. So the eigenvalues of this matrix will be given from this equation, right? So this is the characteristic equation corresponding to this matrix. If you solve this equation, you will find out what will be the values of the values of the eigenvalues of this matrix A. Okay, so you can simply write that lambda I minus A, this one will be equals to, so the determinant, so lambda I minus A is nothing but, so this one will be lambda minus 1 0 0 lambda minus 1 6 11 lambda plus 6. So if the determinant of this matrix is equals to 0, so then you just simply analyze or solve this equation, and you will see that the values of lambda 1 is equals to 1 minus 1, lambda 2 is equals to minus 2, and lambda 3 is equals to minus 3. So we have found out all the 3 eigenvalues of this matrix A. Okay, so next the second step is that you have to find out the corresponding m values. So okay, so that means that, so the model matrix, if you remember that the value of m was equal to m1, then you had m2, then you have, so in this case you will have only till 3. So m1, m2, m3. So you have to find out this m1, m2 and m3. So for finding out m1, we have to find out the corresponding cofactors of this matrix. So m1 will be equals to c11, c12, c13. Okay. So from here you can find out using the cofactor formula, you can find out the value of m1. So m1 will be something like this. Okay. So m1 corresponding to lambda 1. So corresponding to each eigenvalue, we will find out all the values of m1. So m1 will be corresponding to lambda 1. Then we will find m2, which is corresponding to the second eigenvalue lambda 2. Then we will find m3. So similarly, in the similar way, we can find out the value of m2. So m2 will be equals to 2 minus 4 1, and m3 is equals to 1 minus 3 3. Okay, so m1, m2, m3 is known, so you can write this value matrix m. So m will be equals to 1 minus 1 minus 1, then m2 is 2 minus 4 1, then you have 1 minus 3 3. So now we have found out this model matrix. So in the next step, what you will do is that you have to find out the inverse of this matrix, then you have to multiply that with b, and you will get the value of b bar. So once you find the value of b bar, so I'm just writing the expression, you can simply calculate or do the matrix multiplication and find out the value of this b bar. So this one will be equals to 1 minus 1 and 1. So here you see that all the elements of this matrix, they are non-zero values. So that means we can say that the system is completely controllable. Okay, so now you see that we had to go through multiple processes in order to find out what will be this matrix B bar, and then finally comment on the controllability. Now, if we use if we use the Kalman alternate Kalman test, so we'll see that using that Kalman test, it is much more, the computation becomes much more easier. Okay, so the Kalman test says that if you can compute the matrix, so the alternate method, that is the Kalman test, it says that if you compute the composite matrix QC, where QC will be equals to B, then AB, then you have A square into B, right? So if you can find out this matrix, the rank of this matrix, if the rank of this matrix is equals to 3, so here the value of n is equals to 3. So if rank of QC is equals to 3, then the system is completely controllable, otherwise it is not. Okay, so you can simply find out what will be the value of AB. So AB will be equals to, you just simply multiply the value of A with B. So AB is equals to 0, 1, minus 6. Okay, and A square B will be given by 1 minus 6, 25. Okay, so now you can write the value of QC is equals to 0, 0, 1, 0, 1 minus 6, 1 minus 6, 25. So from here you see that from this matrix, basically you see that the rank of this matrix, so rank of QC is equals to 3. So this is equals to the n. So that means the rank, and how would we find the rank of this of a matrix? So rank of a matrix is basically defined as the maximum number of linearly independent rows or columns that are present in the matrix. Okay, so if you have a matrix A, and let's say that the matrix A is an n cross n matrix, if the determinant of, so if you have a matrix which is like, let's say A is n cross n, don't confuse A with this A. So this is just a random example. So if you have a matrix A which is an n cross n matrix, now if the determinant of this matrix is not equals to 0, then the rank of A is equals to n. But if the value of the determinant is equals to 0, then we say that the rank of A is something less than n. Okay, so from here, so here you see that the determinant of this QC, so determinant of QC is not equals to 0, it's a finite value. So that means the rank of the matrix will be equals to n, and the value of n here is 3. So that means we can say that the system is completely controllable. So here you see that using this Kalman test, actually it is it's a much more simpler way of finding out whether your system is completely controllable or not. Okay, clear till now?
Yes, ma'am.
Okay. So now we'll look into the observability of a control system. Okay. So similarly, so the observability comes from the second question. So that means if we know the output of the system for a finite length of time, if we can predict the input or the initial state of the system from those known output, if that prediction is possible, then we say that the system is completely observable. Okay. So now let us say that similarly you have an nth order single input linear time invariant system. So this is the state equation, x dot is equals to ax plus bu, and this is the output equation. So output equation is equals to y equals to c into x. So similarly what we'll do is that we'll again, since this is the non-diagonal, so A is non-diagonal matrix. Okay, so similarly if you want to make it diagonal, so you have to use this linear transformation x equals to mv, and we got the similar, so v dot is equals to delta. This is the expression that we got. In the previous case also we got the similar expression. So, and the output equation will become c into, so output will be equals to, so y is equals to cx, so that means y will be c into m into v. Okay, and this you can express it as this. So c bar into v is equals to y, and this you can simply expand it in this form. So c1 v1 plus c2 v2 till cn vn. Okay, now this we can write basically when you have, now since we have done this diagonalization. So diagonalization, what happens, or the basic property of diagonalization is that it decouples the states. Decouples the states means that from one equation you can only get information about a single state of the system. So that means that so if you know the information on one state, so it would not contain the information of the other states. So you can say that since diagonalization, it decouples the states. So now no state now contains information about the other states. So all the states must be, that means that in other terms you can say that all the states, if they are independently observable, then that means that for every state you have correspondingly one equation. Okay, so a single state equation will contain, or a single state equation will contain information about only one state. So it will not have information about all the different states, since it is a diagonal matrix. If it were not a diagonal matrix, let us say, for example, let's say that if x dot is equals to something 1, 2, 3, 4 into x plus some b into u. Okay, So let us just forget about this. So here if you write x1 dot, so x1 dot will be equals to x1 plus 2 into x2, or sorry, x1 plus 3 into x2. Similarly, x2 dot will be equals to 2x1 plus 4 into x2. So here you see that for every differential equation, it has component of all the states. But now if you make this this equation or if you diagonalize this matrix A, so now let's say after diagonalization you get a matrix something like 6 0 0 5 into x. Now if you write the equation, so you will get x1 dot is equals to 6 into x1 and x2 dot will be equals to 5 into x2. So that means here we have actually separated or we have decoupled all the states, and we have every equation, every single differential equation will have information about that particular state only. So in the previous case, this first differential equation also it contained information about all the states. The second one also contained information about all the states. But in this case, the first differential equation, that is x1 dot, will have the information about that corresponding state variable only, that is x1. There will be no other component for the corresponding to other states. So that means we are actually decoupling all the states. So that means, so we can say after diagonalization, we can say that each state, if we diagonalize each state, means that each state must be independently observable. Okay, so that means that if you want a state to be completely observable through the output y, so we can say that the corresponding coefficient of Ci should be equals to non-zero value. So here we have written that y equals to C1 V1 plus C2 V2 till Cn Vn. So now if you want to find out the effect of V1 on y, so that means that corresponding to that state variable, the corresponding coefficient should be a non-zero value. So if you want to see the effect of V1, so that means this C1 should be a non-zero value. If you want to see the effect of V2, that means C2 should be non-zero value. Okay, so you can say that for a state to be completely observed through the output y, the corresponding coefficient Ci should be a non-zero quantity. Now, if one value of Ci, if it is 0, then what will happen? So that means that the corresponding Vi can have any value. So, but that effect of the Vi will not show up in the input. So let's say that this value of C2 is equals to 0. Okay, so that means that this whatever the value, if the value of V2 is changing, the effect of V2 will not be reflected in the output, right? So that means we can say that this state is not completely observable by measuring the output y. So if we want to measure a state completely, or if we want to measure all the states if we want to observe all the states completely, then all the corresponding coefficients for the variables, that is C1, C2 till Cn, all of them should have non-zero value. Okay, so from a revised statement is that the necessary and the sufficient condition for complete state observability is that none of the elements of this matrix C, which is C equals to Cm, none of the matrix should be equals to 0. If this condition is satisfied, then we say that that all the states in the system are completely observable through the output y. Similarly, there is an alternate test for which Kalman has proposed. So similarly, you have x dot, so the same state equation is provided. So we say that the system will be completely observable if and only if the rank of, we will make another composite matrix, let's say QO. If the rank of QO is n, so QO is basically written like this. So you have C transpose, then you have A transpose, a C transpose, and so on and so forth. Okay, so if you can find out that the matrix of this, the rank of this QO, if rank of QO is equals to n, then you say that that all the states which are present in the system, they are completely observable. Okay, so here also you see that since only two matrices are involved, so only A and So you can say that this A and B will be completely controllable. So this A and B will be completely controllable, or rather you can say then the rank of Q0, if it is equals to n, then the pair A and B is completely controllable. So now there is this duality property which is there for this observability. So if you have a pair of matrices A and B, if they are completely controllable, it implies that the transpose, the pair of the transpose, that is A transpose B transpose, is completely observable. Similarly, if you have a pair AC which is observable, it implies that the pair A transpose C transpose, this will be completely controllable. So this observability and controllability, they are basically they go hand in hand, and they have a duality property which they share. Okay, so now let us take one more example. So in this case you have to find out, so this is the state equation, this is the output equation which is provided to you, and you have to find out whether your system is completely observable or not. So let us try to do it with the Kalman test only, because as you know that this Kalman test is basically much more easier method. So otherwise you have to keep on computing the value of this. You have to compute the value of M and then C and then find out C bar and then see whether the elements of this matrix is equals to 0 or not. So we'll try to analyze the system using the Kalman's test. Okay. So Kalman's test means we have to find out this matrix Q0. So Q0 is nothing but C transpose. Then you have A transpose C transpose. So this is a 3 cross 3 matrix. So we have A transpose squared C transpose. So now if the rank of QO is equals to 3, then the system is completely observable. Right. So now let's try to compute this value of A transpose and C transpose. So A transpose C transpose will be equals to, so if you transpose this A, so you get 0, 0, 0. Then you have 1, 0, minus 2. Then you have 0, 1, 3. Right. And C transpose, so this is your, so this is matrix A, this is matrix B, and this is matrix C. So C transpose is 3, 4, 1. So if you do the multiplication, you will end up with 0, 1, 1, right? So this is also done. So now the next step is to find out this A transpose square into C transpose. Okay, so this will be simply equals to this matrix 0, 1, this A transpose 0, 0, 0, 1, 0. Sorry, 0, 1, 1, right? So this is nothing but A transpose multiplied by, so this will be, this is same as A transpose multiplied by A transpose C transpose. This we have already known, this is equals to this. So this is the A transpose. So you can find out. So this value is equals to 0, minus 2, minus 2. So if you write the value of Q0 or QO, so QO is basically given by C transpose. So this is 3, 4, 1. Then you have 0, 1, 1. Then you have 0, minus 2, minus 2. Right? So, okay. So now you see that the determinant of this, so the determinant value of this matrix is equals to 0. Okay. So as we know that if the determinant of a matrix is 0, so that means the rank of this matrix Q0 will be less than 3. So that means this is not equals to n. So we can say that this system which is provided to you, this is not completely observable. So not all the states of the system are completely observable. You can verify this using that the initial formula also. You can verify in order to find out like which states are not observable. You can verify that using this expression C. If you find this matrix and you see whether all the elements, so you will see that some of the elements of this matrix are equals to 0. So that means that the overall system is not completely observable. Okay. So in a similar way, what you can do is that you can find out whether, so given a proper, given the state equations of your system, or whenever you are expressing your, or you're modeling your system using state space representation. So from the state space equations, that is the state equation as well as the output equations, from those state equations you can find out whether your system is completely controllable or completely observable or not. So depending on whether the you can simply use these tests and you can find out whether the system is completely controllable or observable. So next, so these are some of the practice problems. You can just try to solve them and see. So this one is basically, there are two columns. So this is column number 1, this is column number 2. So this element is -1 and this element is 1. Okay. So simply you can just try to solve these problems, and you can find out whether these corresponding systems are completely observable or not. So it's always easier to use the Kalman method, because this is more the computation or the complexity of analysis is much more easier if you analyze the system using the Kalman test. Okay. So next we'll see something which is known as pole placement by state feedback. Okay, so what is state feedback, right? So before going to what is state feedback, so you can say that this, if you have a control system which is of higher order. So higher order as in, let's say it's of third order or even more, fourth, fifth or something like that. So in that case, if we are using some PI controller or PD controller or other controllers like phase lead or phase lag controller, there are different types of controllers. So this PI, PD, these controller, we have already talked about what is a PI controller, or what are the advantages of using a PI controller over a simple proportional controller. So if you simply have these kind of controllers, then it is not possible to control independently all the poles of the system, because you have only two parameters which you can tune. So if you have a PI controller, you will have there are only two parameters that you can control. You can either control the proportional gain of the system or the proportional band of the system, or you can control the integration time of the system. Okay, so you have only two, so you can say that there are only 2 degrees of freedom. So you have only 2 parameters which can be controlled in order to control the whole system. Okay, so now for a higher order system, these kind of a controller, they are using these kind of controller, it is not possible to control all the poles of the system, because if it's a third order system, so there are, and naturally you know that there will be 3 poles in your system. So that means that, so for you have 2 parameters, but you have to control 3 pole positions. So you can relate that it is not possible to control all the pole positions independently. Okay, so in that case, what we can do is that in those kind of a system, there is this need that if you do need of the state variable control, where what we can do is that we can arbitrarily place poles and this arbitrary placement of the poles, that is independent under certain conditions. Those conditions being that if the system is completely controllable, then we can say that the eigenvalues can be arbitrarily assigned using state feedback. Okay, so state feedback basically it is, or you can say that the state feedback or pole placement, it is basically a method for placing the closed loop poles of a system in a predetermined position in the S-plane. Okay. So let us say that you have an open loop system is given to you, and you want to place the closed loop poles at certain specific positions. And why you want to place that? Because you have to meet certain specific specifications which has been provided to you. That means, let's say that it has been provided that the rise time of your system should be something. The damping of your system should be something. So if all these specifications are provided, so according to those specifications, you have to modify your system. You have to use a feedback mechanism in such a way that the closed loop poles of your system, they satisfy the given conditions for the desired output. Okay, so So naturally, if you use these kind of controllers, then it is not possible. But if you can use a state feedback, so if you can feedback all the state variables which you have found out. So using that kind of a state feedback, what you can do is that you can arbitrarily place the poles of a system, and that arbitrary placement of the pole is known as pole placement by state feedback or pole placement by full state feedback. Okay, so this is what we have already told, that pole placement by full state feedback is basically a method to place the closed loop poles of a plant at predetermined locations in the S-plane. Okay, and the location of these poles, it is directly related to the eigenvalues of the system, right? So we had initially, when we were talking about this state space representation, at that time we have already told that the eigenvalues of this matrix A, they are basically the poles of the system, right? So that means that the location of the poles, it is directly related to the eigenvalues of the system, and this actually in turn it controls the system response characteristics. So depending on where the poles of your system is, the output of your system will vary accordingly. Okay, so what you can say is that the criteria is that the system must be completely controllable if you want to implement this full state feedback. And this full state feedback means that you will feedback, you will provide a feedback path from each and every state variable which is present in your system. Okay, so if you have like 3 state variables in your system, so from each state variable there will be a feedback path, and that kind of a feedback is known as a full state feedback. Okay, so now let's say that if you have if you have a single input, single output system, and it's an nth order state variable, nth order state model. So this will be the state space representation. This is the state equation, and y equals to cx is the output equation. Okay, so state feedback is basically a scalar function, and the form of that function is given by sigma is equals to kx, where k is a matrix k1, k2 till kn, and x is obviously the state variable which is varying from x1 to xn. Okay, so if you see the block diagram of a system with using full state feedback, so this is the system which is provided to you, that is x dot is equals to ax plus bu, and this is c, so y is equals to c into x, right? So feedback means that whatever is the value over here, that is the state variable. So x is basically my state variable. So if you feedback all the state variable using a suitable gain, you can say, and you feed it back to the system input. So this kind of a feedback is known as full state feedback, because the input to this gain is basically all the states which are present in your system. So x is basically all the states x1 till xn. So all the states are coming as an input to this gain k, and using that a feedback is being provided. Okay, so now here if you have, like, let's say this is the plant, since this is the plant, so the input to the plant is, let us say, u, and the system input is something else which is r, right? And the feedback is actually provided and it is compared with the system input. Okay, so you can say that the value of u will be equals to nothing but u is r minus k multiplied by x, right? So x is the input over here. So here you will have sigma. So r minus sigma is equals to u, and where sigma is equals to kx. So the value u is equals to minus kx plus r, where r is basically your plant, your system input, and u is the plant input. But you see that this kind of a system is an ideal system, you can say. So if you want to see it from a practical point of view, this full state feedback is not a practical option, because initially when we started talking about the state variables, that time we had told that all the states are basically not necessary that all the states can be completely observed, or it is not necessary that the state variables that you are choosing, you can measure all the state variables. Okay, so so from a practical point of view, the full state feedback is not a practical way for implementation, since it is not possible to measure all the states. And if you can't measure all the states, then obviously you won't be able to feed them back to the system input, right? So for that, what you need to do is that, so you can write the expression. So x dot is equals to ax. So the first equation was that x dot is equals to ax plus bu. So u will be substituted by this. So ax plus b into minus kx plus r. So this will be equals to a minus bk multiplied by x plus br. Right. So if the pair, this pair, matrix pair A and B, if the matrix pair A and B is completely controllable, then the eigenvalues of A minus BK, so this matrix A minus BK, they can be arbitrarily assigned by full state feedback. Okay, so this, if you can measure all the states in your system, then that is very good. There is nothing better than that. You can use the full state feedback and finally and you can place the poles properly at the desired or predefined positions. So if you know all the states, then from this equation you can say that the eigenvalues of this matrix A minus BK, they can be arbitrarily assigned by full state feedback. So now let's consider a system, or rather we'll talk about this in tomorrow's class, because there is not sufficient time to do this solution. Okay, so we'll revise a little bit about this pole placement in tomorrow's class, and then we'll continue discussing on this. So that's all from my side. So if you have any doubts, you can ask me.
Ma'am.
Yes.
Ma'am, actually, sorry, ma'am. I said you to keep the quiz on Monday, ma'am. On Monday we have another quiz. I forgot about it, ma'am. Please, can you keep it on Tuesday, ma'am? That quiz is also common for A section and B section, ma'am.
Okay, so no later than Tuesday, because
yes,
then because anyways we don't have much time left, and we have to take 2 more quizzes. Like this module will also be over, like maybe probably by next week or early next week we will be finishing this module also. Yes. So we have to take more quizzes. So you're saying that so that is 29th, right? 29th from 5:30. That's okay, right?
Yes, ma'am.
Okay, fine. So let me just talk with the other faculty, and then I'll confirm it.
Yes, ma'am.
Okay. Yeah. So do you have any other doubts?
No, ma'am.
Okay, fine. Then we can end today's class here, and we'll meet again tomorrow. Thank you. Thanks.